All right, the last lesson of Unit 1, we're going to be looking at rates of change, and these rates of change will be average and instantaneous. These are going to be very important for the rest of the course. We will look at rates of change throughout pretty much every unit. For the sake of the video length, we will not be using Desmos to explore the concept. We'll just go through the note. A rate of change is a measure of change in the dependent variable with respect to a change in the independent variable. What does this remind you of? Well, it reminds us of grade 9, 10, 11, the slope formula. Okay, if you don't remember the slope formula, in order to find slope in a linear line, it was y2 minus y1 over x2 minus x1. Okay, these are the differences in y's divided by the differences of the x's. It's exactly what we're talking about. Okay, there are two different kinds of rates of changes that we'll be looking at. The average rate of change, graphically, it is a secant line. Okay, so if we have a graph and there's a parabola on the graph, so it's finding the rate of change between 2 points. So the slope between these 2 points, that is called a secant line, one that goes through the graph. Algebraically, it will be plugging in an x value into the function, finding a solution, subtracting the solution if you plug in a second x value into the function, and then dividing by the difference of those two x values. Okay, it's the slope formula. The difference in y1, so y1 subtract y2, divided by x1 subtract x2. Okay, so average rate of change may be a little tricky because you haven't done it in a while, but hopefully it comes back to you just as a slope formula. We're just using functions in order to find it, not specific points. Instantaneous rate of change, this is the new thing for you. It is the tangent line on a graph. And the tangent line, if we draw our parabola here, is a line at one specific spot. So it just grazes that one spot, a specific x value on the graph. So it's what is the slope at that one point. It's instantaneously changing at a different amount each time, so we want to know it at one specific point. And algebraically, we're not actually going to worry about the second one, but it is the f of x plus h minus the f of x divided by h. And h just represents a very small amount that we're going to add to x. And we'll look at these more in depth. I typically add 0.001 to whatever x is, and I think that's a pretty good, gives us a pretty good idea of what the instantaneous rate of change is. Okay, so we get into it. Average rates of change, or what we call AROC, from a table. So the table contains data relating the height of a golf ball, S to t, in meters with respect to the time in seconds after the ball was struck. Okay, and we can see the table, the time in seconds, 0 to 8 seconds, the height in meters. Determine the average rate of change along the interval of 1 to 2 seconds. What does the AROC mean? Okay, so we're just looking at 1 to 2 seconds. There's not really filling in anything from the function. We don't actually know the equation of the function. We're getting specific points. So it wants us to use 1 to 2 seconds. Okay, so we have, let's do f of 2, take away f of 1, all that over 2 over 1. Okay, so at 2 seconds, the ball is 58.8 meters. At 1 second, it was 34.3 meters. And of course, we know 2 minus 1 is 1. 58.8 minus 24.3 gives us 24.5, and anything divided by 1 is itself. So the average rate of change from these 1 second to 2 second is 24.5 meters. So the A rock from 1 to 2 seconds is 24.5 meters per second. Okay, and that's, what does the AROC mean? That's what it means. It's changing at a rate of 24.5 seconds within that 1 second of time. Okay, determine the AROC of interval 2 to 3. So now we're using the 58.8 and the 73.5. And why is it different? Okay, so we're plugging in 3 seconds, subtracting the 2 seconds. So we have 73.5 minus 58.8 over 1. And we get an AROC of 14.7 meters per second. Okay, and why is this different? Well, this is not a linear line. The ball doesn't just keep going up and up and up forever and ever. It is most likely a quadratic, so it's slowing down. So the ball is increasing at a slower rate than it was from 1 to 2 seconds. Okay, so it just slowed down. It's starting to get to the vertex and be on its way back down. Okay, AROC from an equation. Suppose that the height of the golf ball at any time t in seconds is given by the equation negative 4.9 t squared plus 39.2 t. Determine the AROC along the interval of 1 to 2 seconds. Okay, so it's the same thing. This time, though, we have functions to use. So we're going to use the first, or put 2 into the function first. So negative 4.9 times t squared plus 39.2 times t. And then we'll subtract, doing the exact same thing, but with 1 being replacing the t's. And it's still 2 over 1. Okay, when we figure out the first function, so when time is 2 seconds, that's when we get our 58.8. When we work through the function, when time is 1 second, we get our 34.3 dividing by 1. So it's actually the same as the above. This time it's just not the table, it's the actual equation. So we get 24.5 meters per second. Determine the AROC along the interval of 3 to 2. So it's the exact same thing. We should get the same answer as above. 39.2 times 3, and subtract the whole function at 2 seconds. Okay, the 3-second function gives us 73.5. 2-second one we've already done, 58.8. And like above, we match the 14.7 meters per second. What is different about the process? Well, to be frank, it's a lot more work. To fill in and find the solution from an equation, or the equation. Okay, instantaneous rate of change. We have to get a bit creative when finding the slope of the tangent line. Why? Well, because when we're finding the slope of a line at one specific x value, the slope will result as undefined unless we add a slight increase to the x value. So what that means is if we were to use the AROC formula, so the slope formula, but with just one x value, you would, if the x value was 2, your denominator would be 2 take away 2, which is 0, which is undefined. You can't divide by 2. So that's why we need to add something, and that's the h that I was talking about in the algebraic way to do IROC. Okay, so let's look at this as in a table. So interval from A to B, to estimate the slope of a secant line that resembles a tangent line for the functions st equals negative 4.9 t squared plus 39.2 t when t equals 3. Okay, so the difference, the interval is, in the first one is 3 to 3.5 seconds. So the difference of t is 0.5. Okay, when you plug 3.5 into the equation, we get 77.175. When you plug 3 into the equation, we get 73.5. Okay, so the difference in those is 3.675. And 3.675 divided by 0.5, so the s represents the y's, the t represents the x's, we get an answer of 7.35. Okay, so the IROC would be 7.35 if we did AROC with a difference of 0.5 seconds. If we did 0.1 seconds, so a difference of 0.1, that's our denominator. Plug in 3.1, we get 74.431. We still have our 73.5, giving us a numerator difference of 0.931. And when you divide it, you get an IROC of 9.31. So the difference was 0.931. Okay, if we decrease it, so simplify the h value, so the part that we're adding to 3 even further, now we're doing 0.01. Plug that in, we get 73.6. to go with our original 73.5, and our numerator difference now is 0.1. And 0.1 divided by 0.01 is 10. Okay, what if we add 0.001? This is what I like to do. And in this, not in every instance is it going to be a lot different. This one is actually going to be the exact same. But just trust me, the more decimals you add, the more accurate your answer will be. So we have 73.51 from 73.5, giving us a difference of 0.01. Divide them out, and we still get an IROC of 10. And what if we add 0.0001? It's the exact same IROC of 10. So for this specific example, adding 0.01, 0.001, or 0.0001, we got 10 as the IROC for all of them. It just worked out that way. So I'll let you decide. I typically like to add 0.001 as my H value. But what are we understanding from all of this? The closer the difference of t is to 0, so the smaller it is, the more accurate the solution will be. Whoa. Okay, not a lot of room here, but suppose that the height of the golf ball at any time t in seconds is given in the equation, okay, the equation we've been working with. Determine the IROC at 1 second. Okay, so I'm just going to quickly go through this. So at 1 second, we have negative 4.9. Remember, the H that I'm adding is 0.001. So T plus H will be 1.001 squared plus 39.2 times 1.001, and we will subtract all of the exact same thing, but this time it's just a t of 1. Okay, and our h value that we added, 0.001. When I work out the first function, it's going to be 34.3293951. The second function, when t is just simply 1, we get 34.3. And gives us an answer of 29.395. Okay, why did I use so many decimal places? Sometimes the difference in the two when you're using IROC will be so different that maybe it's just the 5th decimal place that is off. Everything else is identical. So you want to use as many as you can. I mean, don't go crazy with it. But yeah, we want to be as accurate as possible. Okay, what about when t is 4 and then we see that y there, so we know something's going to be weird. So negative 4.9, again I'm adding an h of 0.001. So we have 4.001 squared plus 39.2 times 4.001. And we'll subtract doing the same thing when t is 4. Again, we'll divide by our h value. Okay, the first function Actually, we'll just do it all at once. And we will get an answer of negative 0.004. So it's really close to 0. When our IROC is 0, that represents a turning point, so a maximum or a minimum. So this is a turning point because the IROC is 0.